Welcome back to ECE 441A, 541A. Our exam is Friday. Hopefully that's not a shock. Practice exams are on D2L. Your homework number 2 is due on Wednesday, and you can turn that in the 3 different locations, either in class, online, or in my ECE mailbox. And those all have different times that happen or that are available to you. Lab number 1 should be up and running in terms of we've assigned teams and we've matched those teams with particular systems. If you want to sign up, you should be able to sign up at the stockroom, which is in room 351 of the ECE building. Today what I want to do is start with a quiz, and this quiz you will hand in. I want to see how you're thinking or what your thought process is. I'm trying to get you up and ready for the exam. It's only going to be 2 minutes, but I want your name, and then I can... You're going to be doing a lot in 2 minutes. And then we'll start looking at system identification for underdamped second-order systems. Here's your quiz. I want you, there's 2 questions. The first one is cheer number 1. The second one is cheer number 2. If you get the cheers mixed up, that's okay, but just describe one of the cheers and the second cheer, and why is it important, or tell me about it, each of those different cheers. So cheer number 2, what does cheer number 2 tell us? Cheer number 1, why is cheer number 1 important? You have 2 minutes. And if you're playing along at home, online, you can pretend to complete this exam. Obviously, I won't be asking for your submission of that exam or that quiz. I have other ways of communicating with the online students. Someone commented that that wasn't fair. This entire class is designed to be fair. And I was hoping you wouldn't look at your notes. And it's supposed to be this learning science, retrieving stuff from your brain is very helpful. So I'm trying to get you to remember, and then after the fact you can go back and figure out where you messed up or didn't mess up. I don't care if you get the 2 cheers mixed up. That would only be critical if we were doing it in unison. You're doing it individually, not as a team. We're down to 30 seconds.
I don't have to go first cheer.
All right, time is up. Go ahead and pass those to your right. And we will now start with second order system identification. And we are concentrating on underdamped systems. And last time, I could have asked you, what did we talk about last time? And I think at the very end of class, we started looking at this particular transfer function, which we're labeling capital Y sub A of S. I hope we're better organized on Friday relative to quizzing. But here is y sub a of s. And if you were doing your homework this weekend, you're learning, you should start to understand what the inverse Laplace transform of capital Y sub a of s is, or what little y sub a of t equals. And that's this exponentially damped sine wave. Following instructions. And last time I was corrected on A and sigma. It was sigma and omega sub d. We have a real part of minus sigma. We have a imaginary part of omega sub d. Did we get all the papers? Thank you. And that particular set of poles that are complex conjugate tell us a lot. And I'm hoping you're starting to see the structure that arises when you have poles at those two locations. They have a complex part or an imaginary part, and they have a real part. And in this case, the real part is in the left half S-plane, which gives rise to this minus sigma t, which decays exponentially with time, and the sine part gives us this oscillatory behavior. Whoops. What's this one look like? Now, if you look at y sub b of s relative to y sub a of s, what is the distinction? Is the denominator different? The denominator is exactly the same. The poles are going to be in the same location. What's different with respect to y sub a and y sub b? We have a zero now, a real zero. This is a linear factor in the numerator for y sub b. We now have a linear factor in the numerator, which gives us a real zero at minus sigma, and that now gives rise to a cosine that's exponentially damped. The poles are giving you exactly the same frequency, omega sub d, and they give you the real part, or the exponential decay, in this sinusoidal behavior. And what do we have for a pole pattern now, or a pole zero pattern in the S-plane? Capital Y sub b of s, you could think of this as being a impulse response from a system that has that as its transfer function. But we'll get there in a minute. What I'm trying to help you with now is just to associate poles and zeros, or denominator factors, or denominator expression, relative to what it looks like in the time domain. And in this case, we do have a zero, but we also have those same two poles at minus sigma plus and minus j omega sub d. We have the two poles, and those give us our exponential decay and the cosine. And what does that look like if we had to draw it? If we needed to draw it, we could sort of do it in stages. We could say, oh, we have this is our exponential decay, and we also have a that's supposed to be a periodic cosine waveform. This is now the cosine omega sub dt. But we're actually multiplying those point by point with each other, which now tells us that the actual response for y sub b of t, and I'm not going to get this right, but the oscillation is dictated by the damped frequency, omega sub d, and the shrinking or the collapsing of the oscillating waveform is influenced by the decay piece, the e to the minus sigma t. And so if you wanted to try to envision what's happening, the omega sub d gives you the up and down. You could now look at the period of this. And you could find that from either the two mins or two maxes or any two consistent locations on that oscillating waveform. And you now know that omega sub d is 2 pi f sub d, but f sub d is related to the period, so this is now really, you might see it as 2 pi over t sub d. Which means if you could measure the time duration, the interval of time between the peaks or between the valleys, you could now use that t sub d because you know 2 pi. That's 6.28 approximately. You can divide that by 2 pi, and now you have the frequency, the damped frequency of your oscillation, just by inspection of the waveform. And you could find when this maybe gets to 1% of its final location, and that would give you this exponential e to the minus 5. And from that you could find really the reciprocal or sigma. Because you know e to the minus t over tau could be associated with e to the minus sigma t, and you know at 1% you're at 5 time constants. At 2%, how many time constants is that? That's 4. So you could eyeball it and try to say, okay, I'm within 2% of where I'm going. Now I can say that's 4 time constants, and I can now find or approximate the sigma based on inspection of that curve. That was B. This was A, and look at the particular numerator. The numerator now is exactly the same value as your damped frequency. And if the numerator was something else, you could factor the omega sub d out and figure out how much scaling you have relative to that sine wave, exponentially damped. Here, you have exactly s plus sigma. And if you had something different, you would have to arrange it such that you could maybe factor out an s plus sigma. With that said, what does the following curve look like, or waveform look like, if we now had some generic A times S plus a generic B, but downstairs we had S plus sigma squared plus omega sub d squared. Where are the poles of y, capital Y sub c? They're exactly where they were for parts A and B, minus sigma plus and minus j omega sub d. So it must be looking like an exponentially damped sine or cosine. Which is it? Did everyone catch that? I heard sort of a mix. Well, it is a mix. It's a mix of sine and cosine, and it depends on what A and B are. If we looked at the numerator, that's AS plus B, but we're actually trying to make that look like some amount, let's say alpha 1 of S plus sigma, and some amount of omega sub d. So we're trying to identify or piece together the fraction of that numerator that's representative of an exponentially damped sine wave, that would be the weighting beta sub 1, and how much of this AS plus B is creating the exponentially damped cosine. That's our alpha sub 1. And if we simply do the distribution of alpha through that, we can identify how much of those fractional pieces of the exponentially damped cosine and exponentially damped sine we have. We just need to equate coefficients on the left and on the right. Meaning, if we looked at the coefficients of the S term, what's on the left? Coefficient scaling S is just A, and what coefficient is scaling S, or coefficients, are scaling S on the right? So that was easy, wasn't it? Now we know we have a amount of the exponentially damped cosine. That's our alpha sub 1. And equating the constants, or the coefficients of the s to the 0 term, we can find out how much of the exponentially damped sine we have by solving for beta 1. We have b on the left, and on the right, alpha 1 sigma plus beta 1 omega sub d. And we are interested in beta, or beta sub 1, and that's just b minus alpha 1 sigma over omega sub d. Now we know exactly what the time domain waveform looks like associated with capital Y sub s. We now know that y sub c of t is alpha 1 scaling on the exponentially damped cosine, which was e to the minus sigma t cosine omega sub dt, and it was beta 1 scaling e to the minus sigma t sine omega sub dt. Now, keeping all of those pieced together in your mind might be a little bit of a challenge, but we have the same exponential decay and the same damped frequency of cosine and sine, and this is why you did your trigonometry. Now you can combine those sine and cosines into either a cosine or a sine expression, and you'll just have a time-shifted exponentially damped cosine or a time-shifted exponentially damped sine. Meaning we could rewrite this, and this is just a function of applying your trig identities for the sum of sine and cosine. You could say, oh, I could view that as some a1 e to the minus sigma t, because I can factor out e to the minus sigma t from both of those terms up above, and then I have some fraction, alpha 1 of cosine, and I have some fraction of sine, beta 1. And I can put those together and create cosine omega sub dt. It's the same frequency. I haven't changed the frequency, plus some phase shift, b1. Or, if you liked to sketch sines, you could view that sum or combination of cosine and sine as an exponentially damped, time-shifted sine wave. Let's step it up a notch. Here's D. Let's now look at the inverse Laplace transform of some alpha bar over S times S plus sigma squared plus omega sub D squared. Question? Okay, in both of those, in the blue equations, just above the dashed black line, on the argument of the cosine and sine, those are supposed to be b's. B is in bear, not beta, as in a Greek letter. So, yes, those, I need to work on my penmanship. Uh-oh. My first grade through sixth grade teachers would be upset at me, wouldn't they, for my sloppy penmanship. But those are b's in the arguments of the cosine and the sine. And now what we want to do is look at what's the time domain expression associated with this mess in the curly brackets. But what do we already know? The denominator looks pretty warm and fuzzy, doesn't it, in the square brackets? You've seen that in the previous three. So you know you have poles at minus sigma plus and minus j omega sub d, and anytime you have poles there, you get these exponentially damped sines and cosines. The frequency of the sines and cosines? Omega sub d. The damped frequency is omega sub d. The exponential decay is dependent on how far those poles are into the left half plane. The further they are into the left half plane, the faster that exponential decay. Now, if you wanted to think about this, you could say, oh, y sub d of s could be a g sub d of s times a u of s, where the u of s, or this is a step response of a system. Now g sub d is what I'm now circling with that dashed blue line. This is now a step response. You've now, think of this system, g sub d of s, which could have come from a cheer, right? This could have come from a state space representation, and you now found the transfer function based on c times si minus a inverse b plus d. I think that was cheer 1. Or it could have come from a block diagram, and the basic block diagram is g over 1 plus gh. That's cheer number 2. Right? Rah, rah. So you can find these transfer functions fairly easily. But now think of this as you have a system that has two complex conjugate poles and some constant in the numerator. This is your system. What is it? It's a underdamped second order system. And you now are not shaking it, you're pushing it. You're applying a step input to that, and that's what you're going to do in lab number 1. You're going to push that mass, and it has a spring and a dash pot attached to it. It's underdamped. You'll push it and let it try to get to a steady state. Then you'll release the push, and it'll come back down to a steady state. You'll push it again, and it'll bounce around, and then you'll release it. And you'll do that 3 different times. You're trying to see this step response behavior. And we want to know, what is the structure of the time response? If you looked at this and applied some of your limiting concepts, you could do a final value theorem to this. You know the system is stable, right? The g sub d of s is stable because you have poles in the left half plane. You now, if you push a stable system, what's going to happen eventually? If you push and it shakes, but it's damped, It will eventually come to a stop, maybe at a slightly different location, depending on how you've pushed it or how hard you pushed it. Meaning, what is one part of this y sub d of t time domain expression? If you're pushing it with a constant, and let's say it's a mass spring damper, or maybe it's a second order RC circuit, and you apply a constant voltage to that, what happens to your capacitors? They reach a final value. And what is that final value? It's not moving or shaking, is it? It's constant. Initial or finally, right? So this is I'm finished. My penmanship is being aided, isn't it, by technology. Oh, it didn't go too far, but we don't play ASU for a while, do we? Doesn't that sort of look like... never mind. Now that probably just erased everything above, but we'll see. So that's what I was trying to put. A sub d. It's a constant. But what do we know is going to be a result of those two poles at minus sigma plus and minus j omega sub d? What did we learn in those first three examples? It does shake, doesn't it? You know the frequency that it's shaking. What's the damped frequency? Omega sub d. And how fast does the shaking quit? It depends on the sigma, doesn't it? So now we are going to have a plus b sub d e to the minus sigma t sine, let's just choose the sine, omega sub dt plus c sub d. A time shifted, exponentially damped sine piece of that waveform. If you now needed to sketch that, maybe you are having a conversation. Yes, question? So this structure for the time domain response could be found if you simply did the mechanics of a partial fraction expansion of inverse Laplace transform in capital Y sub d of s. What I'm wanting you to do is to be able to look at some of these pieces and immediately sort of get a feel for what's going on. If somebody said, oh, I have an underdamped second order system and I've applied a constant input to it, wow, you can go to town. Now you can sketch this kind of a transfer function. You can write down, oh, it's going to have this time domain behavior, and they're going to say, I don't know what you're talking about. Well, a picture is worth 1,000 words, so you sketch the time response. What's that going to look like? It's going to be something like that. Where is it headed? This will eventually be a sub d. The second piece of that two-part expression is going to vanish with time. As t gets big, e to the minus sigma t collapses that term down. But what can you tell me now about that exponential damping? What's influencing that? That's the sigma, isn't it? And you can also look at this time interval between maximums or minimums, and that's now t sub d. You can also identify when it first peaks, and maybe I'll do that with lowercase. Maybe I'll say that's little t sub p, the peak time. And we are going to now use those pieces of information to find the damped frequency. Now what I'm saying is you go into the lab and you kick the system. Don't kick it, but let the system kick itself, and so it moves over and shakes, and you'll be able to capture this data. You now have this data. You want to now find A sub D. You can find the period and you can find the peak time, and from that you're going to identify this transfer function G sub D of S. You're doing system identification. Omega sub D is 2 pi F sub D, which is 2 pi over T sub D. Meaning, if we want, or if we know, this time domain behavior, y sub d of t, we found it somehow, you've gone into the lab and measured it. What we want to know, can we find this, what we are calling g sub d of s, some alpha over s plus sigma squared plus omega sub d squared. That's the underlying system. Once we see that, and you'll see that a lot of systems, even if they're fifth order, sixth order, they behave like an underdamped second order system, and you might now collapse all of that mess down to a second order transfer function, a G of S that has this structure. And then you can start designing controllers based on that simplified behavior or model of this more complicated system dynamics. Or what can the different parts of y sub d of t tell us about G of S? And let me just make these three statements now so that you can be thinking about them as we move forward. You could, from y sub d of t, you could identify its final value, the capital A sub d. And we will show that that's actually related to what piece of the transfer function? Can you guess? It's a constant. It's the DC gain of our transfer function, isn't it? It's what G is at time or at frequency 0. So this is related to the DC gain of G of S. And if we've parameterized G of S this way, can you find the DC gain? Yeah, just set S equal to 0, and that's now alpha over sigma squared plus omega sub d squared. And you would need to be told how hard you hit the system, what was your step input, and with that and this model and A sub d, you could now back out the DC gain of your transfer function. Question?
Are we not worried about that extra factor that's
So what happened to the S in this original expansion for y sub d of S? This S is actually there because of the applied step. Now slide down just a little bit, and this is where I was trying to justify that additional S. This mess inside the curly brackets is really a combination of two pieces, a system, G sub d of S, and an applied input, a constant, and I'm just saying capital A over S. Capital A is somewhere mixed up in that alpha bar. But the S is that S that's sitting there by itself in the denominator, or together with the complex conjugate poles, which are a part of the second order underdamped system. Did that help? We are now trying to back out that underlying system, the G sub D of S, or the G of S, which has this structure. And we've said that one part of that we can find is the DC gain, and use that to our benefit with applying A sub D and knowing what the value was that you hit the system with. If I gave you that time domain response, could you calculate omega sub D? If somebody sketched that, could you measure omega sub D? Yes, indirectly. You can measure the distance between peaks. You can measure the period of that damped oscillation. That's T sub D. In the lab, you may have so much damping that you can't identify that second bump. And so we will base quite a bit of our discussion on the time to peak. But if you see some bumps, you can measure the distance between them. And that's T sub D, which now gives you omega sub D. And that says then that once you have omega sub D, which is found from the damped period of oscillation, or we will also learn that omega sub D is related, as I said, to the peak time. And finally, we can look at how quickly we go towards that steady state. How quick, how much time, 5 tau or 4 tau, depending on 1% or 2% tube that we get to our final value. That's going to give us our damping, our sigma. This is then related to the settling time, or the damping, which is also related to the percent overshoot. Yes? So if you have a signal, the question was, how do you find tau? How do you find sigma from this? How do you find tau from sigma? Now, let me just wrap this up and then I'll answer. So this, has everyone watched the Demo 1 video for Lab 1? Is all of this starting to seem similar? Now, the question was, where or how do we relate sigma and tau? You've seen this before, e to the minus t over tau. And so now we look at e to the minus sigma t, and we just compare the exponents. So now we're looking at t over tau is the same as sigma t, or sigma is 1 over tau. So if you found the time, the settling time, and you said, I'm interested in the 1% settling time, you've now found indirectly tau because you've now measured 5 tau. You've now found tau, you've now found sigma, all just by looking at inspecting that time domain response. Now, if your head wasn't spinning enough with betas and Bs and Cs and Ds, let me mix it up a little bit more. Let's do an exercise on system terminology. Here's our system, G of S. And we're saying that that's alpha over S plus sigma squared plus omega sub d squared. And we can think about some of those pieces of G in our frequency domain S-plane plot. Here is minus sigma. Here is J omega sub d, and here is minus J omega sub d. And a lot of times we will just concentrate, since the mirror image is happening below the real line, let's just focus on what's happening above the real line. It's symmetric, or it's a mirror image. This distance is omega sub d. This distance is sigma, but that's also related to our damping ratio times, whoops, not omega sub d, but our natural frequency, omega sub n. So if somebody said, what's the damping ratio? That's that sigma. We'll get to that in a minute. But where did omega sub n come from? Omega sub n, what color do I want to pick? It really isn't that involved. Omega sub n is actually the hypotenuse of the right triangle, formed by the horizontal distance sigma and the imaginary distance omega sub d. This distance of the pole from the origin is omega sub n. That's the natural frequency. Omega sub d is the damped frequency. So that's a zeta. That's another, so zeta is the damping ratio. That's zeta. And that's actually related to, I told you I was mixing it up. I put it in a blender and now we're mixing. Theta. Can I give you any more terms? But theta now is the angle. You can measure that with your protractor if you wanted to. You could draw this and you now have theta. So if I gave you this picture, you can find the cosine of theta in terms of sigmas and omega sub d's and omega sub n's. What is the cosine of that angle theta? Adjacent over hypotenuse from your trigonometry. The adjacent is zeta omega sub n. What's the hypotenuse? Omega sub n. So now you have a way of finding that damping ratio zeta by simply looking or measuring that angle theta. So if you now have these complex poles, you have sigma and omega sub d, you can plot that x. But from that, you can now create or measure theta, the angle. You now have your damping ratio zeta.
So, it's the same as sigma.
Pardon? So it's the same as sigma over omega sub n. Because zeta omega sub n is sigma. That's the real distance. Or you could now, if somebody gave you the damping ratio, which is actually related to the percent overshoot, you could say, oh, I know now the angle relationship between the real part and the imaginary part of those complex poles. Meaning, let's look at how we can parameterize this transfer function a little bit more. We had alpha, and then we had S plus sigma squared plus omega sub d squared. And if we simply simplify the denominator, we now have alpha over S squared plus 2 sigma S plus sigma squared plus omega sub d squared. But that's also equivalent to the numerator over s squared plus 2 zeta omega sub n s plus omega sub n squared. So you might see a underdamped second order transfer function parameterized in terms of zeta, the damping ratio, and the natural frequency omega sub n. But that's the same if we simply start looking at pieces. That's just the Pythagorean theorem. A squared plus b squared is c squared. A squared being sigma, sigma squared b omega sub d plus omega sub b squared, omega sub d squared is the hypotenuse squared. And this is just sigma. Sigma, the real part of our pole, is zeta omega sub n. So I can give you a lot of different information, pieces of information, and you can now extract or create this transfer function from measured physical information, a step response of an underdamped second order system. You know how to obtain sigma. How do you get sigma? From the settling time, or maybe from the damping ratio, right? Percent overshoot. What about omega sub d? That's just the frequency of oscillation. And then tying all of that together is finding the DC gain. You can find that from where you end up, given how hard you pushed the system. Saying that a little differently, you're now trying to impress whoever it is that you're eating with. You now have a system, an underdamped system, G of S, and you say, here's the output, and here's the input. Can you tell me what the output is in terms of the system and the input? Yes, right? That better be trivial. Y, no, the letter Y, Y of S is equal to G of S, R of S. And we are going to be, when we're trying to do system identification, we are simply using a constant input. So R of S is going to be, let's say, A over S. This is the amplitude that we're applying to our system. And if we've now parameterized our underdamped second order system, you can write down a parameterized form for the transfer function. That's alpha S plus sigma squared plus omega sub d squared. And the input is A over S. Question? So now, what happens when you Laplace transform a constant in the frequency domain? What does that produce? It's 1 over, if it was just a unit step is 1 over S. A constant A, you Laplace transform as capital A over S. So in the time domain, you apply a constant. In the frequency domain, that's now capital A over S. Is that what you were asking? Yes, so now we're applying a constant in the time domain, and what we want to do now is try to connect even more this transfer function parameterized form and the time domain expression, and we'll pick up at that point on Wednesday.